Cities has evolved over time through the lens and hand of human-centered design approach. This in turn has led to urban ecologies being unbalanced with no other intelligence incorporated into the equation except our tongue. The result can be clearly experienced and seen in all our metropolis with the rise in health issues, overcrowding of our transportation networks, and limited public space. New technologies has become embedded in our society over the past 10 years, are starting to reshape how we use and experience the city. They have started to generate a new collective intelligence amongst us humans, but they have also started to revival other urban actors' intelligence. Sensing, tracking, and monitoring device has started to show us humans' intelligence of bees, frogs, plants, trees, and other ecological agents within the city. This computational paradigm shift led us to ask the question, could an interface that combines all the urban ecological actors' intelligence help guide the development and reprogramming of the city? Mochen seeks to find a new balance between how we design future cities through a combination of human and ecological intelligence, using advanced machine learning to mediate the needs of both urban participants. The design will go through three parts. Feature learning. This part will reconstruct the existing urban plan by transforming and synthesizing the common feature of urban and natural landforms in the pixel matrix. Simulation-based verification. Human and animal behaviors will be speculated based on the matrix map. The data will record for redistribution of space. Metadata to materialization. Spatial distribution of metadata will be transformed with materials and design based on the adjacency requirements. Feature learning uses unpairing data in machine learning. Its main contribution is to help us find common and different features in unrelated data, and alternate unique feature from one to another. We pixelate the natural and urban plan while retaining the original architecture layout, adding more natural features into the public space. After training the machine, we got the synthesized site by the generative neural network. The result shows that under the existing urban context, if we want to approach a high biodiversity nature landscape materials, we need to provide more waters and 13% green space within the urban, and dilute the root area down with 21%.
Previous feature learning allows us to extend the testing area for urban mobility and rethinking the relationship between movement and space. These urban mobility represent different forms of intelligence, from human and machine movement to the animal migration paths. We start with collecting existing data. We use the pedestrian distribution point on the site based on the Twitter API. By using space syntax, which is based on the spatial visibility and connectivity, we set these points as origin to test and simulate the movement pattern on the site. Through this simulation, we get a crowded area on the test ground. At the same time, we explore the impact of different urban functions on the pedestrian movement with different daily schedule. We also test the behavior on the extended public space that has been redefined through the feature learning, which allows us to have a better use of the public space rather than just focusing on the road network. In terms of the vehicles, we set up a logic follow the agent-based algorithm to simulate the movement of the particles. By adjusting the parameters of flexibility and collisions, those vehicle behavior can be translated into personal autonomous vehicle and cycle. Follow the previous feature learning, we look into the urban animal behavior by the different preference of the spatial features. We translate the preference of the spatial features of different animals into resistant map. It's a way of converting spatial cognition into data and create a link between the land features and the numbers. By using Circlescape, which based on the electronic theory, we find the least cost path by inputting the different resistant map. Different from the shortest path, least cost path will be the most likely road for migration in the long term. Here some simple demonstration shows how they work with different spatial features. Based on these tests, we get the most likely migration corridors for different species on the site. This preparation can help us to set up our movement data, which represent different forms of intelligence from humans and their pedestrian networks to the automation linked to the London mobility plan, passing from other species' ecology corridors and their paths. These data can be translated into parameters, values, and trusted forms of algorithm ties in with a relational understanding of space and time. Then, we think the entire site as an ecology adapting system, which can be both natural and artificial. They are independent units of materials, information, and energy flows on the network. Input all that information into the network and achieve meta-intelligence. So based on these discussions, we set up our interface. After inputting weighted data into interface, these data will be translated into values and parameters which can be evaluated to fit into different scenarios. The interface will give a score for those output value based on the different requirements. And if it doesn't meet the demand, the suggestion will be given to the user for whether the space shall grow or demolished. Each data can be read as different values on each grid of the network. We can weight these values by multiplying weighting factors. By using machine learning, clustering can help us to redefine the space in multiple categories. Each group of input data has its own adaptability, representing its own intelligence. The weight in the interface represents equity, whether you listen to the other type of intelligence and design with compassion. Such method might provide us a fair suggestion for all the agents among the many possibilities under a certain scenario. This is a more humanistic and enlightened attitude, which make it possible for us to make voice for animals even within the COVID-19 pandemic. We can test through the simulation tools, finding whether the space is enough for commuting and activities. Once we update the new data, it will suggest us to open up some of the urban blocks. After getting the agent's data, we also look into the environment layer of the site, which can be the noise, water catchment, solar condition, and NDVI. Then, we can read the data through the different vectors in the analysis network, such as agent value, environment value. These metadata can be used to help understand the context in which data is created and used, as well as learn the relationship and how to communicate with the data. The resolution of the metadata can be also compressed through the different data vectors and can be even increased. Through the different values of the description of metadata, we can sort the data and find unseen relationship behind the data. Data points are the frozen moments that shows us the different possibilities, and values point to the fact that something is held to deserve its importance or worth of something for someone. In last step, we try to materialize from the metadata. Under the influence of time and space quality, we predefine the urban surface and explore the spatial proposal under the joint decision-making by multi-intelligence. We analyze the behavior patterns of different species. Hunting, inhabiting, and moving of animals match various material preferences. Under the guidance, we explore the classification and the connection of different materials. Considering the scale of different species and the solar, noise, moisture parameters in the metadata, Wallace's genetic algorithm is used to find suitable surface and classify them according to the changing tendency of the shape. The design lists the category of material to different intelligence, differentiate the naturalness of the material according to the different characteristics of man-made, mixed, and natural, and analyze the NDVI value of each material. Similar for human and autonomous vehicle intelligence, different facility and infrastructure correspond to the size of the intelligent density and the functional requirement. The combination of material change with the environment, helping us to actually predefine the site. We can see the result are reshaping due to how the data change and how we filtrate. We analyze activity points in different locations to reshape the entire urban surface. Therefore, it presents a predefined for urban design involving multiple intelligence. In this way, what we are doing is rethinking the AI. The AI not only learns from human intelligence, but also the other type of intelligence, the meta-AI.